All right. So Wednesday, we left off talking about how to generate chirality, like how to make chiral molecules. And we said that one way was to do what we call asymmetric catalysis, and that's to use a chiral catalyst or a transition metal with a chiral ligand chelated to it, and then use that to create an environment around the metal and around the reactive site that forces creates some bias in the transition state during the course of a reaction. All right, and it's the same here. We're using a pre-existing stereo center, right? If you got a molecule that has a chiral center already in it, like the one we had here, where you have a chiral center right here, that chiral center is going to dictate the outcome of the reaction. So over here in the products, you're actually going to get both products. Let me just copy this right quick. Right, you'll get both products. One where that methyl group that was added is going back, and then one where it's on the same side. And I'll explain that in a minute. Right? But you're not going to get the same amount of each one, right? So that's why when you use this method, and that's the goal anyway. The goal of doing asymmetric synthesis is to favor one stereoisomer over the other, just like we talked about with Paxlovid. You want one stereoisomer out of 64, right? Like we talked about. And so here you're going to get both of these products, but they're not going to be in equal amounts. So that's what this concept is here, where you take something chiral and react it with something achiral, and you get what's called a mixture of stereoisomers. So you're going to get some R and some S, right? If you do, and if you watch the video that I sent, if you do two achiral things, then you're going to get what's called a racemic mixture. What does that term mean? And somebody who watched that video that I sent out, what does racemic mean? Equal parts R and S. That's if you just take two achiral things, and that's what you expect. You expect if you take two achiral things and react them together, and you're making stereoisomers, then you expect, since there's no bias and there's no way to differentiate the two pathways to get to R or S, then you should get an equal mixture, right? But the concept that we're going to focus on is the one above it, where we look at taking something chiral, reacting with something achiral, and then generating an unequal mixture of stereoisomers. So I have a mixture here, but I should have qualified that. It's an unequal mixture. Right, so you're going to get more of one or more of the other, depending on what the reaction is, and also depending on how the bias, like how much bias that pre-existing chiral center actually creates. So let's go right into one of the problems right here. And then we can go back to here and answer these questions as well. All right. So let's go to the problem here. And you already have this handout, or you should already have it. And can somebody read that for me? Just unmute and read through that problem so we can kind of parse it and see what we're looking for.
Is it hydroboration? Sorry, okay. Yes. Hydroboration oxidation of R-trimethyl
You can skip that part.
Okay. Study yields two stereoisometric products in differing amounts. A, which product would you expect to be formed in the highest amount? B, what is the relationship between the two products? C, explain why the products are formed as an unequal mixture of stereoisomers.
All right, we can start with, thank you. We're going to start with C and answer that first, right? Why do you get an unequal mixture of stereoisomers in this case? What have we done, right? Notice we have a molecule that has a pre-existing chiral center. So if that's the case, what outcome should we expect? We should expect on the product side an unequal mixture right? We should get an unequal mixture because we took something chiral, reacted it with something achiral, and because we've done that, the outcome of that is automatically by default, you're going to get two stereoisomers in an unequal amount, right? And that amount and the ratio between those two is going to differ based on how much influence that pre-existing chiral center has on the reaction itself, right? So when you see a ratio like this, 80-20, a percentage like that, there's a term for that, and we call it the product distribution. I'm going to abbreviate product. Right, that's what we call a product distribution. Anytime you do a reaction that's competitive, where you have the potential to make more than one product, you're going to have a distribution of products. So we just call it the product distribution. Right, it's just a ratio of products. And this abbreviation is PDTS, is an abbreviation for products. So don't get hung up on that part. All right. So C, explain why the products are formed as an unequal mixture of stereoisomers. The reason is because I started with a chiral molecule that had a pre-existing stereocenter, and I reacted it with something achiral, and it gave me an unequal mixture. It should give me an unequal mixture because that's what we have up. That's what we set up here. If you start with a pre-existing stereocenter, that's something that's chiral, you react it with something that's not chiral, you're going to get a mixture of stereoisomers, and it's going to be unequal, right? The inequality depends on two things. What two things determine the extent of the product distribution? Like, somebody help me with that. If you watch the video that I sent out, you should be able to answer that. Anybody? Did y'all start Labor Day early? Is that what it is? All right. So the inequality between the two products, it's going to be, go ahead.
I got your cheeseburger. Package. Package. Is chirality one of them?
So the chirality is going to force it to be unequal. So I agree with you there. But there's something about the actual group at the chiral center that causes the ratio between those two products to either be really, really disparate or be really close. And it's really based on the size of the group and the proximity of the group to the reactive site. All right, so those two things kind of determine how far apart the two products are, like how imbalanced the ratio is. Let me say that. right? It's going to be based on the size of the group and how close it is to the reactive site. All right. If you did not watch the video that I sent, I recommend that you watch it, because otherwise this probably sounds like Chinese or Greek to you. So let me move this to another page, because we're going to answer. Well, we can answer B before we answer A. Let's answer B, because the answer to A is a little bit more involved, and I want to put it on a separate page so I can show you this whole idea about a bias in the transition state and so on and so forth. So let's answer B. When you look at those two products, what are they in relation to one another? What I mean by that is in terms of stereoisomers, are they enantiomers? Are they diastereomers? Are they the same? Like what's the relationship between those two products?
Aren't they the same?
So let's look at it.
Wait, no.
So here's my chiral center. That doesn't change, right? And then if you look at the stereo center that's set as a result of the reaction, is that the same? Like
No.
one is coming out of the page, one is going back into the page. Is that right?
Yeah.
But what are they, mirror images?
No.
They're not mirror images. So what's the the term that we use to describe stereoisomers that are chiral but are not mirror images of one another?
Diastereomer.
Good, excellent. They are diastereomers. So that'll be the answer for B. That these are diastereomers. Right? And we know that because number one, they're not mirror images. But then number two, you can look at the two stereo centers and see that they are, like, you only changed one, right? Going from product A to product B, you only change this stereo center right here. Right, the other one stayed the same. All right, questions? Any questions?
No, sir.
All right, let's do this. Let me cut this out, because we want, in order to answer, well, I kind of gave you the answer to A. If you look at the ratio, we can see that product A is formed in 80% yield and product B is 20% yield. But let's take that further, because we need to explain why. And so I want to take this and put it on a different page. All right. How many of you remember this reaction from organic 1? Hydroboration oxidation. Anybody remember that from part 1? Especially if you got an A or a B, or even if you got a C. This is a reaction that you should remember. Anybody?
No, I don't remember.
Okay. Thank you for your honesty, by the way. I appreciate it. So hydroboration oxidation, let me give a quick review of that before we start talking about why this reaction did what it did, right? If you remember from part 1, right? If we take a double bond, I'm just going to take this one, and it's not symmetrical, and we treat it with BH3, right? It goes through this intermediate alkyl borane, where the hydrogen adds here to the more substituted side, and the boron adds here. That's the hydroboration part. Hydro, because I added hydrogen. Boration, because I added a boron to the other side of that carbon in that double bond. So that's the hydroboration. And then in the second step, you can look up here, you can see it's 2 steps, right? There's the hydroboration, you run that, and typically what you do is set it up. You would either use a syringe pump or add the BH3 because it's a liquid. You syringe it in, maybe you go grab a sandwich, you come back to the lab, and then you perform the second step, which is the oxidation part. Right, so in the oxidation part, that's where you take that boron and you actually substitute it out. It's not really a substitution in the traditional sense, but it is in the sense of substituting the boron with the oxygen. It's a pretty involved mechanism too, but this is where your oxygen is going to come from here, from the hydrogen peroxide at H2O2, right? That you see up here. So your OH group is going to come from there, right? It's really almost like an organometallic type mechanism where you add the hydroxyl, you need base in there. You add the hydroxide. I'm sorry, the peroxide to boron, and then it's a rearrangement that occurs between the carbon boron bond and the boron oxygen bond. So it's a very involved mechanism. But the point is that you get a alcohol and the alcohol is what we call anti-Markovnikov. Anybody remember that term?
No, sir.
It means that the OH adds to what we consider on the double bond the least substituted side, right? So here, this is a CH2, and then that's a CH, right? But it also has a methyl group attached to it. So this is the least substituted side. And this would be the most substituted side. There's some other nuances to this mechanism as far as why the boron adds the way it does, so on and so forth. All right. So the question for our reaction is, why do we see the results that we see? All right. So that somewhere at some point when that boron adds, right, it's going to be influenced by that stereo center. So I'm going to, and then the actual rearrangement that happens also, that has to happen as well. So let me take a piece of this. I'm going to just take this. So here's my chiral center that's already present. I think it's O silicon with 3 methyl groups on it. And here's the double bond. Right. So when we think about this, if you look at that, right, there's a hydrogen here facing out. When you look at that, what do you see? Right? Which, if you had to pick a side to add to avoid the chiral center, which side would you come from? Right? Think about it in terms of the H is kind of coming out of the page, and this big group right here is going back into the page.
The left.
So let's think about it in terms of front and back. So the H is on the front and the other group is on the back. So which door would you come through?
The front.
The front door, exactly. So what we have in this case, because of that chiral center being where it is, right, now that means that the back face is blocked. All right. That means the back face is blocked. So when boron comes in to do the hydroboration step, right? And I'm just going to draw this in terms of, let me scoot this over. When you do the hydroboration step, that boron is going to recognize the fact that the back face is, and I'm speaking in terms like molecules are sentient, they're not. It's just the lowest energy pathway. All right, so when I add in BH3, right, that's going to come in and it's going to attack the front face. Let me just read, I'm going to copy this. I always use this same idea of the chiral center being like a guard dog. And if you got a dog, if you ever been, when I was a kid, my friends had dogs. I hated dogs. All my friends had dogs and they were all aggressive. And if the dog is chained up to a tree in the front yard, you might want to go to the back door to avoid getting bit, right? And so when you think about that in terms of this, right, that boron is not coming from the same, it's not going to come from the same side where the group already is, right? So it's actually going to attack. And let me change this because this is, I'm trying to illustrate a transition state. So it's actually going to attack when it attacks. So I'm gonna draw it like this. So it's coming here, and then the electrons in that BH bond are going to come here, right? So in the transition state, there's going to be a bond here and a bond here. So this is boron, this is hydrogen, but all of this is on the, so all of this is going to be happening on that front side, not on the back side, right? So in the intermediate is going to look like this. Let me just copy this and I'll edit it. And I know that's cheating because you're probably scrambling to write it. Right, but over here, this is what my intermediate is going to look like. Right, this is going to be on a wedge. So is the hydrogen. It's going to be on a wedge, right? Because the boron is trying to avoid, again, coming in from the same side as that chiral center, that, or the same direction that the chiral center is facing. Can somebody tell me what that, if you watch the video, what is it called? What am I trying, what is the boron trying to avoid in this case? There's a specific term that chiral center creates. And when that happens, it increases the energy of the pathway. Anybody? There's a specific term that we use to say what boron is trying to avoid. Right, so it's trying to avoid what we call steric hindrance, right? A steric interaction is bad because it's going to make the energy of the pathway go up. Now, what about the other pathway, right? Because this is occurring on the front face. And then by the same token, if I go through a similar transition state for boron attacks from the back face, my intermediate is going to look like, let's paste it in again. What would that intermediate look like if boron attacked from the same side where the group is, where the chiral center is? Wouldn't it be going back? So this is the other intermediate.
Dr. Russell,
Go ahead.
can I ask why, if the difference between the spatial arrangement of the, like why does that create the steric hindrance? Is it just because the energy is maintained differently for that arrangement than the other arrangement?
Yeah, good question. So look at the group. The group is facing back, right? And think about this in terms of when we think about in terms of chemistry, right? If you have a group that's here on a wedge, and you have a group next to it, those the space between these groups, the less space that there is between the groups, the more unfavorable it is. So that creates what we call steric hindrance. And so the ideal situation would be for those groups to be apart from one another because of the sterics, right? So anytime you put groups close together, it's going to create steric hindrance, and that's going to give you and add it. It's going to add to the energy, right? And that's not good. Chemistry is always, anytime you do chemistry, you're always seeking to go from high energy to low energy. So you don't ever want to do anything that's going to cause the energy of the system to increase, right? And so when this arrangement between boron and this group is the preferred arrangement, just simply because they're further apart from one another. That's a great question. And then down here, what do we see that's different? Right now they're on the same side because both of them are going back, facing back into the page. Is that right?
Yes.
Right. So this is energetically unfavorable. I just put higher energy. Anytime you raise the energy, that's bad. Right. That molecule prefers to exist in the lowest energy conformation possible. So anytime you make the energy go up, it's bad. Did that answer your question?
Yes, it really did.
Okay.
Yeah.
All right. So now, now we see why the ratio is what it is, right? Because if you look at the two products, A, the OH is on the opposite side, right? And then in product B, the OH is on the same side. So which one of these two, and I know I'm kind of getting in the weeds a little, but which one of the two intermediates is going to give me A?
You said which of the two intermediates is going to give you what? Sorry.
Product A, where the OH is on the wedge. If you compare those two.
The first one you drew where we
Yes.
put, yeah.
So we'll call this, let's call it A1. And then this will be B1, right? So this is going to give me product A. Right, where you have that the two groups opposite to one another, and so the level of, well, the amount of steric hindrance is less and the energy is lower. Right, so this is the low energy pathway. Right, and then the other intermediate where the two groups are on the same side, this is going to be the higher energy pathway, and it's going to give you product B. Let me finish this statement. So it's going to give me product B, and this is higher. This is going to be higher in energy, right? So when you look at the chiral center, if you notice, it's right next to the reactive site, right? The reactive site is here. Right, and then your chiral center is adjacent to it. right? That matters. The closer the chiral center is to where the reaction is happening, the more it's going to influence the outcome of the reaction. The further away it is, the less it's going to influence the outcome of the reaction. By the same token, the larger the substituent is on the chiral center, the more influence it'll have over the reaction. And we'll talk, I'll write all that down before we stop. But I want to go to the next example because it's a similar example. It's just a different reaction. And there's one subtle change in the reaction. And because of that, that's going to change the outcome. It's going to change the ratio, the product distribution. All right, let's go back to any questions about what we just talked about first before we go to the next example.
Not for me.
All right, let's go to the next example. And this really draws on your prior knowledge of part one. Remember, I said you had to have a working knowledge of part one. This kind of draws on that. But if you look at the reaction, it is, somebody look this up since, because yeah, somebody look it up, oxymercuration, and tell me what that reaction does. It's really in the same class of reactions as hydroboration, but there's one thing that's different about it from hydroboration.
Online says it's an electrophilic addition that transforms
Keep going. That's you get ready to say the main part.
an alkene into a neutral alcohol.
Good. That's the same thing we did up here, right? Alkene is a double bond, right? So you take an alkene and you turn it into something else. As a matter of fact, if I know that there's probably nobody here from my class from 21, last time I taught it, because I teach it once a year. But if you took the summer class, you've seen this, and you've seen the whole cachet of reactions of alkenes, right? You can take a double bond and turn it into all different types of functional groups, just depending on what you react with it. So down here with oxymercuration and hydroboration, both of those turn alkenes into alcohols, but there's a difference in the regiochemistry. Right, it did. So we said a minute ago, hydroboration was anti-Markovnikov. Oxymercuration has Markovnikov regiochemistry. Right. Let me give you a really basic example of what that means, because both of these reactions, in essence, you're adding water to the double bond. You add a hydrogen to one side and an OH to the other side. So anytime when you do that, we're just going to say HOH, right? And it's an unsymmetrical alkene, right? If you add the OH to the more sub, I kind of defined that up here too, but I'll put it. Oh, it's here, right? You see on the alkene how you have a more substituted side and the least substituted side. We have that here. So with the with the hydroboration, you add the hydroxyl group to the least substituted side. You can see that over here. With oxymercuration, it's the opposite. You're going to add the alcohol to the more substituted side. So in this case, you're going to have an OH here. This is what your alcohol is going to look like, an H here. All right. That's the extent that I'm gonna dig into that, because that's a part one reaction that I know it was taught, but I don't know how much you grasp from it. But here, let's just look at the reaction here. if you look at that double bond, let's read the question. Who was it? Is it Jaya or Jaya? How do I pronounce that?
Jaya.
Jaya. Can you read this one too?
Mhm.
All right, come on.
Oxymercuration of the same compound produces two products in relatively 50-50 ratio.
Mhm.
Draw the products of the reaction and explain why there is a decrease in the ratio.
Okay, great. So what's the first thing you notice about this reaction? It says that, okay, so up top, the ratio is 80-20. Here, it drops to, I said relatively, so let's just say 54 to 46. It's got to be 100%. So it drops to 54 to 46. So first thing is draw the products. And then the second part is explain why there's a decrease in the ratio. All right, so let's draw the products. Where is the hydroxyl group going? If you look at the double bond, this is without knowing the mechanism, without knowing anything, right? The oxymercuration is a two-step reaction too. You have the mercury addition part, and then you also have a reduction step in the second step that gets rid of mercury. So I'm not going to go into the weeds of that. I actually have I could send you a video that has all these mechanisms in it. But for this right now, that's going to take up all the rest of the time we have. So I'm not going to do that. So let's just do this from a very basic perspective. Which side of that double bond is more substituted? The left side or the right side? Left being this side, and then right being this side. Which side is more substituted?
Oh.
All right, look at the way you tell that. I could tell that there's some trepidation about that idea of substitution on an alkene. The way you tell is the most basic way is to count the number of hydrogens on each carbon in the alkene. So the carbon on the left that's in green has one hydrogen attached to it. The carbon on the right has no hydrogens attached to it. It has only carbons. So this side is more substituted. All right. So for oxymercuration, where's the OH going and where's the H going on the alkene? That's the only thing that's reacting.
The right side is going to have the OH.
Okay, let me see if I can copy it from up here. Yeah, I'll copy it. So you said the right side, the side that's kind of
Most substituted.
more substitute. Yes, the side that's highlighted in orange, right?
Mm-hmm.
All right, good. You're right. You're 100% correct. Let me just crop this, and then I need to do a magic trick right quick. And because the double bond it gets used up. So we don't have that in the product. All right, so the OH is going to be here. So I'm going to draw that OH, and then the H is here. And then on the other product, let me see if I can copy that. Nope. What should the other product look like? Anybody? Is it going to be? The other product should have the OH going in with the opposite configuration. Is that right? So instead of it being up, it should be back. Is that right?
All right, so it's going to be dashed.
Yeah, thank you. It's going to be on a dash, OH. And so is the hydrogen that adds as well, right? Now, here's the question, because this is the easy part. The harder part is, why does the ratio drop? These are the two products, one with the OH on the opposite side of the pre-existing chiral center, which is right here. And then one with the OH on the same side. But the ratio is 54 to 46. So there's no real bias between them. So that stereo center doesn't have as much influence on the reaction as it did in the first reaction. So what's the difference in the two products?
Well,
Yeah.
no, go ahead. Go ahead.
Oh, I was gonna say that the H and the OH are like diastereomers.
Well, it's still diastereomers, but look at where the OH is in the first product relative to the chiral center that's already there.
Mm-hmm.
And then look at where it is in this product. What's the difference? Right, I mentioned a term earlier.
Isn't it steric? So the second one is there's steric hindrance because the OH and the H groups are going in the same direction as near the
Okay, but
other group.
if that was the case, wouldn't the ratio be closer to, well, wouldn't the two products, the amounts of the two products be further apart? If the ratio went down, that means that the level of steric hindrance also went down, because now you can access what that's saying, what that ratio is saying is that you can access both products basically at with the same amount of energy necessary to reach one or the other. Like the energy is basically the same. But what's different about the two products? Where is the OH in the top reaction relative to the OH in this oxymercuration reaction? That's the question. If you answer that question, then the other part of the question is going to be answered.
Oh, is it because the OH is closer to the chiral center?
In the top?
Yeah.
And then on the bottom, it's further away, right?
Yeah.
Come on. So if it's further away, what does that mean? Think about it again, like a dog tied up, to a tree or whatever. If the dog is further away from you, then that dog has less influence over the path that you take. It's the same thing here with the reaction happening further away from the chiral center. What that means is that the chiral center is not going to have as much influence over which way the hydroxyl group is added, right? Because it's further away. So here, and it's not much further away, it's just one carbon. But that's the kind of nuance you deal with when you do reactions like this, right? So here, the chiral center is further away. Put your cash out in the chat, Jaya, dang it.
Jaya.
Yeah, put your cash app in the chat because you solved the mystery. So the stereochemical outcome is less influenced because the chiral center is further away from the reactive site. Right? If the reactive site is here on the more substituted side in this reaction, and that chiral center is further away, then it's not going to have the same effect like it did up here. Like up here, I showed you the boron added immediately adjacent to right next to the chiral center when you had formed that intermediate. Over here, this is a different type of reaction, and the water, which is one of the reactants, right, is going to attack at a location that's further away from your chiral center, right, your pre-existing chiral center. So it's not going to have as much influence. That's the point. The two things that control the product distribution are size and proximity. In this case, we had the same exact starting material and the same exact chiral center, so the size didn't change, but the proximity changed, right? And when we change the size, which is what the next question is, which we got to stop. I'm not gonna go over today, but we'll pick this up on Monday. When the size changes, then not Monday, God dang it, Wednesday. Man, all right. When the size changes, it also changes the outcome, right? It's going to really change the ratio. All right. So I guess, man, I wish we could just finish this, but I ain't gonna do it. I'm gonna stop right here. Any questions? If you did not watch that pre-existing Chiral Center video, and I'm not judging you, but I'm making an assumption. I could be wrong, but the assumption is that not very many people watched it. So if you did not watch it and you watch it after this discussion, then you're probably going to have a better understanding of what we talked about. If you refuse to watch it, then when you see this again, you're not going to know what we're talking about at all. All right, so we're going to finish this up on Wednesday when we come back, and we're probably going to start a new section because it's not going to take us the whole class to finish this on when we come back. All right, y'all have a great Labor Day weekend. Enjoy yourself. Stay safe. Hope to see you at the game if it's not raining. Yeah.
Have a nice day.
All right.
Thank you.
Y'all
Bye.
take care.